computer, just so you know what happens is you probably will notice on the, maybe on the upper left-hand corner of your screen, you might see that it says it's recording. I see that on my screen. It might be because I'm the one who's doing the recording. But I will try to record if I remember every day. Anybody can please remind me. I'll record every lecture and then I'll put them out there. That way, if you missed the lecture, you'll have access to it. If you didn't understand anything and you wanted to go back and view it multiple times, you can do that. So I'll save all of the lectures. And I checked yesterday, it does take a while before the recording can actually be saved to the computer. It took approximately an hour for it to take a roughly 2-hour recording and store it down onto my computer. So in general, I would tell you that recordings probably won't be available immediately. They'll probably be available by the following day. Okay? All right, we're at 11:59 right now. I want to give you a heads up about tomorrow. Our chancellor tomorrow is holding a town hall meeting for all of our employees. We've got some critical information sharing with employees. So we'll be doing that tomorrow. That is scheduled to run from 11 o'clock to 12 o'clock Phoenix time. I will tell you that I know our chancellor pretty well. I think that will cause me to be late to class. So let's just plan on class tomorrow, but expect that I likely will be in that class a little bit later. Okay? So just wait for me to come on. And if it's an issue, and I think we're going to be running too long, I'm doing that one on Zoom as well. If there's an issue, what I'll try to do is I'll try to send an email to let you know that, or I'll see if somebody else can do that for me so that we can get in touch with you and let you know that either A, I expect we're going to be another half an hour, or B, let's just cancel the class for today. We can pick it up during a different lecture. Okay, does that sound good? Okay, Jordan, I'm going to put you on the spot right now. So thanks to those of you who sent me your copies of your homework. Jordan, there were some things that you had questions on the homework. So go ahead and unmute as you're talking.
So it was question 1. I started it, and like I said, I had that weird gut feeling that I wasn't doing it right.
Excellent. Okay, question 1. Let me get to question 1. I got the book in front of me here. And this was in chapter 7, correct?
Yeah.
Okay. So question 1 gave a circuit and wanted information when the switch was moved. So let's just quickly draw the circuit so everybody knows what we're looking at. Hopefully you'll be able to see all of this. If you can't, let me know that you can't see a circuit that I'm drawing. Five ohms there. Here's the switch. The switch opens and T is equal to 0. And then we have a resistor down the middle. That's a 2K resistor. This is I2. I1 is in this direction here. There's I1. Another resistor. This one's 6K. And then over here, a 400 millihenry inductor. Okay, so that's the circuit, and the value of the source is 40. And here's what we're asked for. Find I1 at 0 minus, at 2 at 0 minus. Let's start with part A. So A is I1 at 0 minus and I2 at 0 minus. Good? So at 0 minus, what position is that switch in? Is the switch up or is the switch down?
Down.
Excellent. So the switch is down. It looks like this, right? Just going to pull out an eraser here. I'm just going to erase right now. We've got that. Here we go. So this looks like that. That's what the circuit looks like. What's been going on? This circuit's been running for a long time, right? It's been the circuit has the switch has been closed for a long time. So what does that mean? The switch has been closed for a long time.
It's in DC steady state.
Excellent. It's in DC steady state. What does that mean I can do to something in the circuit? What can I do to what?
You could replace the inductor with its equivalent model.
Excellent. So its model. So here we go. I'm going to erase it. There is an inductor there. But what is its model in DC steady state? What does an inductor look like in DC steady state?
It's a short.
Short circuit. There we go. So we're just going to put that short circuit right there. So this is our circuit. Now, I1 and I2 are pretty easy to solve for because all we have is a circuit that is a standard, simple DC circuit. And in fact, we have a variety of different ways that we can do this. We can use mesh analysis. We can use nodal analysis. We can combine resistors if we want to. What is your preferred method? Let's do nodal analysis. That'll be easy, okay? So I'm going to do nodal analysis. Here's my reference node in the bottom. I'm going to make that my reference. And right here, I'm going to call this one V. I'm just going to write my one nodal equation. Here we go. V minus 40 divided by 500 plus V over 2K plus V over 6K is equal to 0. Common denominator, 6K. So we'll just multiply through by 6,000. So when we do 6,000 divided by 500 is 12, right? So this is going to be 12, V minus 40, plus 3V plus V is equal to 0. So we have 12V and 3V and another V, 12V and 4V. I think that's going to give us 16. 16V is equal to, bring it to the other side, 12 times 40, and I'll just leave it like that. You can see that 4 goes into this 4 times and goes into this 10 times, and then 4 goes into that 1 time and goes into that 3 times. Clearly, V is equal to 30. So the voltage here at this node, I'm writing at the node, is 30 volts at that node. Everybody good so far?
Yep.
All of this is at 0 minus. Remember, this circuit we're staring at is at 0 minus. So help me find I1. Do you agree that I1 is equal to V divided by 6K? Is that correct? So that's going to be 30 divided by 6K equals 30 over 6. 30, make that look like a 30 over 6 milliamps. And 30 over 6 we know is 5 milliamps. So 5 milliamps is I1 at 0 minus. This is particularly at 0 minus because this circuit is only valid at 0 minus. Good on that one?
Yep.
Then I2 at 0 minus, well, all of this is at 0 minus, is equal to V divided by 2K. So V we know is still 30. 30 over 2K. 30 over 2K is 15 milliamps. So those are our answers at 0 minus. That's the answer for part A. All right, everybody good in part A? Chime in if you've got an issue. I'm just going to slide this up and take this particular circuit. We want to do the same thing at 0 plus. Now, if I'm going to draw the circuit at 0 plus, it's going to look like this. So right now, this is T is equal to 0 plus, and my circuit looks like the following. Notice how cool this pad is that I'm using. I don't know if you noticed it. It took my ugly circle and formed it into a very nice circle for me. That was really nice. I love that. So the switch is now open. The switch is open. And all we have is this exciting part of the circuit right here. This 2K resistor, this 6K resistor, and over here, this 400 milli inductor. But what do we know? We know that IL at 0 minus equals IL at 0 plus. And we already solved for 0 minus. So let's go back here and remember at 0 minus, this I1, everybody see that I1 right there? That is the same current that's flowing through that inductor. So we know that I1 at 0 minus is equal to I1 at 0 plus. So in this circuit, because this current must be the same, this is 5 milliamps, we know that this one is 5 milliamps. So the first part is easy. I1, let me get that right in my circuit. I1, yep, that's I1. I1 is at 0 minus equals IL at 0 minus, which equals IL at 0 plus, which is therefore equal to I1 at 0 plus, and that's equal to 5 millionths. So that's I1. Now I2 is this one here. That's I2. So looking at I2, what can we say about this? Well, look, this switch right there is open. So this current is going to be flowing around in this loop right here. So I2 is equal to what?
Minus I1.
Yes, minus I1. So this is at 0 plus. It's equal to minus I1 at 0 plus. So that's going to be equal to minus 5 millionths. Okay, then the rest of this is finding I1 of t for t greater than 0, I2 of t for t greater than 0. And then it says, let's jump to E. Part E says, explain why I2 at 0 minus is not equal to I2 at 0 plus. Well, what would make it equal to I2 at 0 plus? Only if there's a continuity condition that requires that it's the same. Resistors have no continuity condition. Currents through resistors are not guaranteed to be continuous. Voltages across resistors are not guaranteed to be continuous. So I2 at 0 minus is not the same as I2 at 0 plus because the inductor that we had in series with the other resistor is not an inductor in series with this one. And if we had an inductor in series, we would have a major problem with this circuit. We would have just created an impossible circuit. Okay, so now C and D for this one are just to find I1 and I2 for all t greater than 0. Jordan, did you need assistance with that?
No.
Okay, so we're just at that point, we're just using that 5-step method to take the values that we have. If I1 is 0 plus, we apply it in infinity. We'll have to draw the circuit at infinity to get that, correct? When you draw the circuit at t equals infinity, tell me for this circuit, I'm just going to show you t equals infinity. It's going to look like this. Forget what's going on over here. It looks like this over here. A resistor, this resistor, and this inductor now looks like it's in steady state, correct?
Yep.
Here's I1, here's I2. Tell me about I1 at infinity. Tell me about I2 at infinity. What are they equal to? And why? How many independent sources are left in the circuit?
0.
0. There are no sources, there's no current. There's nothing that's drawing current in there. So equals 0. Okay? So now you have the value for I1 at infinity, I2 at infinity. You have the value for I1 at 0 plus, I2 at 0 plus. There's only one more thing that we would need. What other thing would we need to be able to find the total solution?
Time constant.
Excellent. So the time constant is going to be found by looking through here. Here's a resistor, and we remove the inductor and we look through here. So the time constant is found first by finding our Thev. Just as a reminder, this is 6K, this is 2K. What's our Thev equal to?
8K.
Excellent. 8K. And the time constant is equal to L divided by R Thev. So just a reminder, L was equal to 400 milli, that's 0.400. That's divided by 8K. Whatever that number is, that's your time constant. Now you have everything and you're just going to put it in this equation. I1 of t is equal to I1 at infinity plus I1 of 0 plus minus I1 at infinity, that's the number, times e to the minus t divided by t sub c. Amps. That would be your answer. So we already know I1 at infinity, it's 0. So this is 0. We know that is 0. And so this is just equal to, I wanted 0 plus. Help me, remind me what I wanted 0 plus was. That was 5 milli. Michelle, welcome.
Yeah.
So 5 e to the minus t, again, over t sub c, where t sub c is this value right here. Just plug it in there. And this is going to be milliamps. That's what I want is equal to. Okay, Jordan, that helpful?
Yes.
Other comments or questions about that homework assignment? Jordan, was there another problem?
I don't have it with me. I think it was number 4.
Okay.
I think.
So same sort of thing with a circuit. So let's just quickly look at a piece of that, and you can let me know when you've got enough. So the circuit looks like the following. This is problem 7.4. And it looks like, oh, sorry, let's erase that. Get that off. Let's get here. All right, just get rid of that. Back to my pen. So here we go. We have a source here, plus minus 240 volts. Wrong one. So this one is 25 volts, 50 ohm resistor. Here's the switch. The switch closes when t is equal to 0. Note the mistake your author made. Anybody note that mistake? What did the author write in that book?
You wrote I was equal to 0 instead of 2.
Yeah, I was equal to 0, right? Not I equals 0, t equals 0. Hopefully you were sharp enough to recognize that. 200 here. Here's our inductor. This is a 50 millihenry inductor. V sub L is right here. That's V sub L. And this is I sub L. And I0. I0 right down the middle. Okay, so this switch is open, which means the whole middle of this circuit doesn't exist, right? We're not seeing the middle of this circuit at all. It's just one square. In other words, this is all we're seeing. We're seeing this, 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 and now that looks like it's in DC steady state. So that's just a short. So that's what we're seeing at t equals 0 minus. That's what we're seeing. Okay, let's answer some easy questions. I0 at 0 minus. Well, I0 is going down the middle branch. It's this guy right there. What's I0 at 0 minus?
0.
Good, excellent. Now, IL at 0 minus is this one. It's this current right over here. So we'll have to do a little bit of math, put my 50, my 200, and my 25. So see if you agree with this. That this 25 volt source sees 250 ohms connected to it. So the current, this current here coming out of this source, which is the same as IL, so this is IL over here. That means this is IL over here right now. So IL, and this is all at 0 minus, is equal to the 25 volts divided by the sum of the resistors, which is 250. And so that's equal to 110. So that's IL at 0 minus. That's I0 at 0 minus is 0. VL at 0 minus. Remember, here's VL right here. What's VL at 0 minus?
0.
That is correct. It's the voltage across a short circuit. It's 0. So we've got all of those. Now, of all of those that we just figured out, of those three, tell me which ones are required to be continuous so that when we get to part B, and part B says, hey, look at this at 0 plus and tell me what those same values are at 0 plus. What must have the same value? Continuity condition is for what? Voltages, voltages across capacitors. Jack, what is it?
It's IL.
It's IL. Voltages across capacitors or currents through inductors. So we know that IL at 0 minus must be equal to IL at 0 plus. That is forced. So IL at 0 plus is equal to 1/10 of an amp. If we go to our circuit at 0 plus, here it is. So 0 plus, I still have the source. It's the 25 volt source. I have the 50 ohm resistor. Now we put this short is in there. Here's this resistor, 200 ohms. Here's the inductor. And the inductor value is not going to be important to us, but I am going to write here VL across the inductor. The value is not going to be important to us. Let's see why. So we know the following. We know that this current right here is equal to 1/10. If we know that, we can figure out this. I'm going to call this VR2. So what is VR2 equal to? 200 times 1/10? 20 volts? Now, go around this loop. Now, KVL equation says VR2 plus VL equals 0. So 20 plus VL is equal to 0. Therefore, VL, and this is only at 0 plus, is equal to minus 20. Everybody like that? All right, let's figure out what else we need to do. Well, look at this. I'm going to call this here VR1, okay? And VR1, we know through this KVL, oh, I didn't want that to be a circle, hang on. Delete that. It doesn't want to delete that for me. There we go. Let's get it out of there. And let's just put that aside. For whatever reason, it doesn't want to erase. I don't know why it doesn't want to erase. Okay, so we go around this loop here, go around that loop, and we have minus 25, the source. Okay, minus 25 plus VR1 is equal to 0. So VR1 equals 25. Why is that important? Because it allows us to find this current. I'm just going to call that I1. So what is I1 equal to? It's VR1 divided by 50. Is that correct? By Ohm's law. So that's 1/2. Welcome, Arushi.
Hi, I've been here. Sorry.
Okay. You're able to see everything okay? Able to hear everything okay?
Yep.
Good. As I said earlier, I am recording these lectures, so we'll have them recorded also. Okay, so I1 is 1/2. Well, how does that help me? I need this guy right here. I need I0. So look, we know this current. We know this current coming in. KCL says I0, the current coming out, is equal to this I1 minus the amount that goes forward, minus IL. So it's equal to 1/2 minus, what was it, 1/10, I believe. So 5/10 minus 1/10 is 4/10, that's 2/5. So I0 at 0 plus, this is this circuit here, this is T is equal to 0 plus. Remember that, T is equal to 0 plus. That's this circuit right here. So now we have all of our values at 0 plus. Then we can go to infinity. Jordan, should I continue?
No, I think this is good.
You
I
sure?
can finish the rest.
Okay.
Yeah.
Communicate with me via email if you want me to. I can get back with you on this if you want to see the rest of it, okay?
Okay.
It's the same process that we used in that first problem. Okay.
Right. Right.
All right. New topic today. Are you excited? Today, we're working, here's where we're going. So we're going to the world of second order and higher order circuits. And we want to be able to handle more than just two storage elements, or one storage element actually is what we have right now. We want to get to the world of two storage elements and then beyond that. In order to do that, we are going to need to understand complex numbers. And so I'm going to take today and in the next lecture, if I need to go over complex numbers as you need to understand them. I want to pause for a moment and let you know the following. I have been told multiple times in my career, and even when I was a student, as an electrical engineering student, I was told multiple times that, oh, these complex numbers, this stuff is designed to flunk people out of electrical engineering and drop them out of the course. I want to be very clear about this. Complex numbers are a tool that we are going to use. Most of you have seen them, but have never worked with them to the extent that we are going to be working with them. And you're going to have a much, much better and deeper understanding of complex numbers than you've ever had before. We don't use them in the curriculum to flunk people out. That's not what they're for. They are a tool that is going to make the work that we are doing way easier. And when I say way easier, I mean way easier than going the differential equation route, which is what we've been doing. I mean, look at what we've done right now. We're only dealing with first order differential equations, and we've developed this 5-step shortcut method, which many of you will agree is really not much of a shortcut at all. When we have 2 storage elements, the challenge is greater. When we get to 3 storage elements, it almost gets impossible to solve these circuit problems. And so the only way we're going to be able to solve them is twofold. 1, we need complex numbers. And 2, we're going to actually right now in the short term restrict our inputs to being only sinusoidal inputs. So we'll talk about that and you'll see where that plays a role over the next week or 2. Okay? So not by a show of hands, just by sort of just unmute yourself for a moment. How many of you feel like you have a general understanding of complex numbers? And how many of you are like, you know what, I've seen them before, but I really don't understand them?
I've seen them once.
For me, it's like on the fence.
On the fence, okay?
Yeah. Yeah, me too.
Yeah, I agree.
Okay, so we're going to see complex numbers like you've never seen them before. I don't expect that you've seen much of what we're going to talk about, but I am going to start with a general introduction to complex numbers. Let me start that introduction by telling you the following as I write the word complex numbers down, or the words. There is nothing in the world that exists in the complex number realm. Complex numbers were developed by mathematicians to solve challenging problems in an easier way. And if you can remember to keep saying that, you'll be in great shape. So for example, we're going to talk about what complex numbers are in a moment, but you don't go to a store and find something there in the store that is a complex number. You don't find it anywhere in the world at all. We're going to use them as a model. And what we're going to actually do is we're going to model a couple of different things with complex numbers, including resistors, capacitors, inductors, sinusoidal sources, impedances, whatever those are, admittances, whatever those are, and a variety of different other things. We're just going to model them with complex numbers. So once we understand them, we'll be in great shape and we'll be able to do that. To understand complex numbers, we first have to start with why we need them and why some mathematician figured out that we needed complex numbers. And so it started this way, believe it or not. Some mathematician needed a solution to this equation in some work that he was doing. He needed a solution to x squared plus 1 is equal to 0. All of you know that there is no real solution to that equation. And so he had to extend the world to a different realm. And so I'm going to show you, when we talk about numbers, all of us talk about this world of numbers that looks like this. This set is the set of all real numbers. And that's everything that you and I deal with. Those are the rationals and the irrationals. Within the rational numbers are the integers, the natural numbers inside of that. So I'm going to pretend that this little circle right there, let's just pretend that this is the set of reals. I'm sorry, not reals, rationals. So the rationals are inside. Just pretend with me, because actually it's much smaller than that. Then outside here, these are all the irrationals. Okay? And the complex numbers consist of all of those plus this whole huge, larger world. Okay? This is the set of complex numbers, and that's the way we show it, with the C like that, with the complex numbers. So that's the complex number world. Okay? Within that world, some complex numbers are real. Notice that this group right here is inside. It is a subset. So real numbers are complex. These are the ones that we love to deal with. They exist in the real world. But we're going to deal with an extension of the real world. So when we look at this equation that we've had, this x squared plus 1 is equal to 0, all of us know that as mathematicians, we would say this. That's how we start to solve this. And then we would take the square root of both sides, and taking the square root of the left-hand side gives us x, and this is equal to plus or minus the square root of -1. So we need this square root of -1. And we call that, in the world of mathematics, we call the square root of -1 I in the mathematical world. Because I is used in electrical engineering to represent current, in this class, we won't use I. Every time you put an idea, I'm going to cross it down, cross it off on your paper, and write that is wrong. We do not use I in electrical engineering. In electrical engineering, we call this J. So this, for us, would be equal to, it's equal to plus or minus J. Okay? So J is equal to the square root of -1. J equals the square root of -1. I'm going to put that in a box, but I never, ever want you to think of J as being equal to the square root of -1. I just want you to think of J as being equal to J. That's the way we think of it. J is J. I know it's the square root of -1. There are only a couple times when we need to know that J is the square root of -1. You'll see when those are. J is J. Okay? Now, J has some really interesting properties that you should be aware of. And I'm going to show you the cyclical nature of J when we raise J to certain powers. It's really cool. So we have J started by itself, J to the first power, and that's equal to J. J to the second power is equal to, obviously it's J times J, but this is one of those times where I'm going to use the value of J. Here it is, square root of -1 squared. And the square root of -1 squared is -1. So anytime we have a J squared is equal to -1. And every time you see that, it's -1. J cubed is equal to J squared times J, which is -1 times J, which is -J. Bizarre. J cubed is -J. I'm going to show you something interesting about what -J is equal to as well. It's pretty interesting. Okay? So far, so good? Now, here we go. J to the fourth. Well, we can do the same thing if we want to. We can look at this as it's J cubed times J. That's -J times J, which is minus, and then I have J times J. What's J times J? Anybody?
J squared.
J squared, and what's J squared equal to?
-1.
-1, correct. So minus and -1 is +1. J to the fourth power is +1. We have just gone around the cycle because J to the fifth is now equal to J to the fourth times J. which is equal to 1 times j, which is equal to j. Look at this. So guess what happens when I do j to the 6th? J to the 6th is going to be equal to j squared. And so that's going to be equal to minus 1. And so this is cyclical in powers of 4. Okay? So really all we need to know is j to the first power, j to the second power, j to the third power, j to the fourth power. And from those, all you have to do is factor out powers of j. You throw them away. For example, if I had j to the 29th, that's equal to j to the 28th times j to the first, which is equal to j to the fourth raised to the 7th power times j to the first. J to the fourth is equal to, what did we say? J to the fourth, 1 raised to the power, that's really easy, times j to the first power. That's equal to j. So all of those, no matter what power you have, always will filter back down into one of these four, either j, minus 1, minus j, or 1. Everybody good with that? That's all just mathematics. So far, nothing overly scary. Okay, now, a general complex number, a general complex number is written in the following form. This form, I'll put it down for you right now. I'll remind you later. This form is called the Cartesian form. We'll see why. Or the rectangular form. Okay, either one of those, rectangular form or the Cartesian form. Clean that up for you a bit. Okay, here's the form. We represent complex numbers with capital letters. So I'm going to use capital A equals little a plus j times b. So that's the form we use. Now listen to the terminology I used. When we talk about this, we'll talk about this complex number as being a plus jb, even though it's a plus j times b. This is multiplication right there. That's multiplication. But we just say a plus jb. Since it's multiplication, we know I can also write it this way. A plus b times j. And I will interchange, and I will use both of them because you're all smart enough to know that multiplication is just multiplication. I'm just going to pause here for a moment. I'm noticing that we've lost Jack's here, Julian's here, Arushi's here, Marcelo's here, Terrence is here, Garrison, Connor. Great, we've got everybody. Okay, terrific. We're all here. I just want to make sure nobody falls off. Okay, so A plus JB. Okay, here's what's important. You ready? And it's really neat. A and B are real numbers. They are members of the real set of numbers. So I have an A and a B that are complex in and of themselves. I can't have that. So A is real. So here's an example. A equals 3 plus J8. That's a complex number. Here's another example. B equals minus 2 plus J7. Here's another example. C equals 3 minus 3J. Often, when the number that is affiliated with the J term, often when that number is negative, we usually write the number first so that the negative is affiliated with the number. But a lot of people still will write it this way. 3 minus J3. All of them are great. Everybody has their own likes and dislikes. So when we look at these complex numbers, we define them. So here, going back, A equals A plus JB. We say the following. Little a, we know A and B are real. A is equal to RE, stands for the real part, then we use braces, the real part of capital A. A is the real part of capital A. So if I say up here, what's the real part of A? The answer is, the real part of A is? Anybody? Real part of A?
3.
Excellent. Real part of B?
-2.
Excellent. Thank you, Jack and Jordan. Appreciate that. Real part of C?
3.
Good. All right, here we go. Big mistake here. B. Somebody might want to go on mute out there. B is little b. I'm sorry. Hold on. My mistake. We're using the A part here. Let's go back to that. B is the imaginary part of A. This is where students make a mistake. So when I look here again at my A, I say, what's the imaginary part of A? The imaginary part of A is imaginary part of A equals 8. This one, imaginary part of B is equal to 7. Over here, this one, the imaginary part of C is equal to, well, I don't need that. Let's erase that. Don't need that. Erase that. It's equal to -3. Notice the whole sign goes with the number. It doesn't go with the J part. And when we say the imaginary part of A, we don't say it's J8. We don't say the imaginary part of B is J7. It's just 7 or 8. It's just the number and its affiliated sign, S-I-G-N. Okay? So that is the general form of complex numbers that we're going to be using. Now, there's another way to look at complex numbers, and that's in the polar form or in the looking in the Cartesian coordinate system. So I'm going to show you what we do with numbers here, and I'm going to use a ruler here to help me get this nice and neat for you. So let's just do this. Just draw that. And then I'm going to take this and do this. Straighten that out a bit. Settle down. Perfect. Okay. So let's pick a number. A equals 3 minus J2. So when we look in the Cartesian coordinate system, what we are looking at is the following. The x-axis is no longer the x-axis. The x-axis we call the real axis. And the y-axis is called the imaginary axis. Okay? And this is everywhere in the world. The real axis and the imaginary axis. Real is always the x, imaginary axis is always the y. Now, if I wanted to plot what A looks like, I can plot it a couple of ways. And here's one way I could do this. 3 on the real axis, 2 on the imaginary axis there, -2 on the imaginary axis there. So 3 minus J2 is that dot right there. That would be the number A. Most people don't like that, so what they do, and I'm going to do this without the ruler. Oops. Let me just pull that back up for you. Sorry about that. So what they do is they show it this way. They draw that line right there to show you A. Oftentimes, we show it with the line so that you can see it. So A can be shown with the line. The dot itself can represent A. There are a variety of different things that can represent A. But just looking at this, it shows us a variety of different things that we can do. And here's one such thing. There are a number of ways to represent these numbers. Let's take a look at this number, by the way. Let's put in B. Let's let B equal, for example, 2 plus j. So 2 on the real, 1 on the imaginary, that's right there. There's b right there, that's b. Now, each of these can be represented in what we call our polar form. And polar form says to describe this number, instead of using a and b, you're going to notice it's always two things. It's a real part and an imaginary part. Or it's a length, a radial distance away from the origin, a radial distance away from the origin. So for example, that distance or that distance, and the angle measured positive from the positive x-axis. So this way here, that's a positive angle. When we go in the opposite direction, so angles measured in this direction, these are positive angles. And when they're measured in the opposite direction, they're negative angles. So this angle here would be a negative angle, okay? So I'm going to note, call that theta B, and this one, I'm not going to squeeze it in here, theta A, okay? And then here, this distance, we call that the magnitude of A, the distance, the magnitude of A, and this distance here is called the magnitude of B. All right, has everybody got that? So another way we can describe these numbers is by looking at their magnitudes and their angles. Now, I'm just going to pull aside for a moment, just pretend we have this picture. Okay? So here I have A, that's the real part of A. This is the length of A, so this is the magnitude of A. And B is this, that's B, but that tells me that this length here is B. And this is theta A. I think all of you know, but I could be wrong, that we can find this length and we can find the angle through geometry. Is that correct? So here's another way to represent this. So we have A is equal to A plus JB. And another way we can represent it is the following. And this is called polar representation. It's the length, which I'm going to call R, at an angle of theta. The length at an angle of theta. I want you to observe the following. A and B are elements of the real number system. There are no restrictions. R has a restriction. R must be greater than or equal to 0. Does everybody understand that? It's a distance away from the origin. Distances are always positive. The smallest distance it can be is 0. If it's pointing in the opposite direction, like this, for example, that is still a distance away from the origin. So it will have a positive distance. The other thing is we want to restrict our angles. And the way we want to restrict our angles, excuse me, my hand is sitting all over this. That's why that's happening on the pad. So the restriction on the angle is the following. It's minus pi, or 180 degrees, is going to be less than or equal to theta, which is going to be less than or equal to pi. So if I slide this over a little bit, take that back to here. Let's put it right in there. So when we look at this, we can see that a positive angle is going to go from here to here. Once I get from here to here, if I go beyond to here, it's easier just to represent the angle this way. So we use a negative angle. So once we cross over the x-axis on the negative side, we say, don't do that. Take the angle in the negative direction instead. All right? Everybody clear about that? So here we have complex number, rectangular form. A equals A plus JB. Okay? Polar form. A equals R at an angle of theta. That's the way we read that, r at an angle of theta. Now, looking at these two and knowing your geometry, I know that you know that there's a relationship between A, B, R, and theta. And so there are going to be many times when we are going to convert from one system to the other. Sometimes we want to work in the rectangular form, and sometimes we want to work in the polar form. So we're going to write down exactly what those equations are that allow us to convert from polar to rectangular. So first, let me just, right here, r is greater than or equal to 0, and minus pi, less than or equal to theta, less than or equal to pi. Okay. So now let's do the conversions. So we have these conversions for us that are going to allow us to convert from rectangular to polar and from polar to rectangular. So let's go rectangular to polar first. Conversions. Converting from rectangular form to polar form. Okay, go back to the picture if it helps. So if the picture helps, just put one over here on the side. Use this picture, it'll be helpful. This length is B, this length here is A, this is the angle theta, and this is the angle R. So that's nothing more than dealing with this triangle, like that, theta, R, the hypotenuse, A, and B, and this is what we know. R is equal to the square root of A squared plus B squared. So that's one of our equations. The other is theta is equal to the tan inverse of B over A. I want you in your minds forever to be thinking the following, forever. It's the tan inverse of the imaginary over the real. 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 It's always the tan inverse of the imaginary over the real. Okay? So B over A. So these two formulas are the formulas that are going to allow us to be able to convert. If we are in the rectangular form and we want to go to the polar form, we can easily do it by using this. Let's do an example. Example. A equals 3 plus J4. I would caution you here, caution of quadrant. So when you do the tan inverse, if you have a calculator that does the tan inverse and includes the appropriate quadrant, use that. Usually that's an ATN2. That you're giving it two values, the B value and the A value. So you have to be careful because you can get the wrong quadrant. Quadrant 1 and quadrant 3 are going to have the same number in parentheses. For example, if B and A are positive, and if B and A are negative, you'll end up with a positive quantity in the parentheses of the tan inverse. If A and B are both negative, the negatives cancel, and that gives you a positive quantity. So you're taking the tan inverse of a positive quantity. The tan inverse function is only valid from minus pi to pi. I'm sorry, from minus pi over 2 to pi over 2. So it's only valid in that area. So we have to make sure we get the right quadrant. In this class, one of the ways we'll do that is we'll just leave our answers tan inverse of B over A. And so when B is negative, make sure we leave the negative number in the numerator. If A is negative, leave the negative number in the denominator. That's how we will indicate it. All right, here we go. First thing, R. R is the square root of 3 squared plus 4 squared. That's equal to the square root of 25. So R is equal to 5. And it's the principal root because it is a positive quantity. It's not plus or minus. Okay? Theta is equal to, real simple, tan inverse of the imaginary over the real. That's 4 over 3. Done. Leave it like that. I know you have calculators. There are some times when you're going to want to use a calculator to simplify further mathematical work that you're doing. But for the most part, Answers like this are exactly the way I want you to leave it. Tan inverse of 4/3. We can all figure out what that angle is. Again, there are times when simplification, you have multiple angles that you have to add together. That's when you want to actually use the correct angle. Okay, so let's do another example with a negative number in this so you see what I'm talking about. Example. In fact, let's do something very similar. Let's B is equal to, and then let's do it's equal to, for example, -3 plus J2. -3 plus J2. So what does that look like? Just from a picture's perspective, so that you have a picture's perspective, -3 is over here. 2 is there. This is always your real axis, always your imaginary axis. So it's way over here. And you can see we're going to get this angle right here. But the tan inverse function is not going to give us that. The tan inverse function is going to give us an angle that's down over here in the fourth quadrant. Okay? So it won't know, for example, if the angle is over here or over here. It won't know that. So tan inverse, if you punch it in, it's going to give you that angle. You'll have to correct that angle, and you'll have to add 180 to it to get that angle over there. So just some games that you should be aware of. Okay, here we go. For this one, r is equal to the square root of -3 squared plus 2 squared. Notice the beauty, negative numbers, it doesn't even matter when we get the r. The r value doesn't matter. That's equal to the square root of 9 plus 4. 9 plus 4, square root of 13. Leave it just like that. It's the square root of 13. Theta equals tan inverse of b over a. b is 2 over a minus 3. Notice I did not do this. I did not do this. Tan inverse of minus 2/3. I did not do that. So we know in this notation here, that negative number in the denominator is indicating that it is the real part that is negative. If it was the imaginary part that was negative, I would have left the negative sign in the numerator. Okay, so that's a real easy conversion. It's not bad. Okay, if we remember our trigonometry a little bit, we can probably figure out how we do the conversion, right? That's converting rectangular to polar, but how do we do a conversion from polar to rectangular, right? How do we do that? So let's write that down. Converting from polar to rectangular. So that means we're given A equals R at an angle of theta. How do we find B, I'm sorry, not B, same A. So let's just get rid of that there for a second. We want this to be equal to A plus JB. How do we find that A and that B? Okay, so let's go back to the picture again. Standard picture. There. There's theta, there's R, there's A, there's B. For those of us that are pretty good with our trigonometry, and certainly if you've taken physics, you should be good enough at your trigonometry. We know that this is pretty simple. So here's the answer. Let's start with A, the real part. A is equal to, well, actually, let me start this way. For those who might not be real familiar with their trig. Let me start this way. If we look at theta, if I asked to find the cosine of theta, what's the cosine of theta equal to? Well, the cosine is the opposite over the hypotenuse. So the opposite, I'm sorry, is the adjacent, is the adjacent over the hypotenuse, right? So the adjacent side of theta is A. So this is equal to A over R. So if I want A is simply equal to R times the cosine of theta. Okay? The sine of theta, that's the opposite over the hypotenuse, so that's B over R, and therefore B is equal to R times the sine of theta. So what we know is given R at an angle of theta for A, this is equal to the following. I'm going to write it two ways. It's equal to R cosine of theta plus J, now the imaginary part, R times sine of theta. Some people like that. Some people like to factor out. The math that we know is still math. I will let you know when there are variations to the math. But that R is a common factor. I'm going to factor it out. R times cosine of theta plus J sine of theta. And this cosine of theta plus J sine of theta is really important. And if we're lucky today, we're going to understand why that's really important. So we can write both in polar form and in rectangular form. Regardless of which form we're in, we can convert our equations from one form to the other, and those are the magic equations for converting. Let me pause on that and ask if there are any questions with regard to those conversions. Comments or questions? Okay, I want to show you something interesting. So let's just, an interesting relationship for J. And we're going to use this a lot. So it's not just interesting, it's important because we're going to use it. So here we go. You ready for this? 1 over J is equal to minus J. It's a nice thing to remember. 1 over J is minus J. It is so easy to prove. I'm going to prove it to you. It's so easy to prove. I'm going to prove it to you. Here we go. 1 over J times J over J. J over J is just 1. Even though J is this imaginary, bizarre thing, J over J is still 1, is equal to, multiply the numerators, J times 1 is J, multiply the denominators. J times J is J squared, and we know J squared is minus 1. This is equal to minus J. So there's our proof that 1 over J is equal to minus J. And we will utilize that. It'll be pretty important for us to utilize that information. So it's a nice feature. We'll see that it plays a role with our capacitors, our inductors, and when we're doing, especially when we're doing nodal analysis, it comes in very handy. Okay, now here's where I want to go. I just want a temperature check. How many of you feel like, oh my God, this is bizarre? And how many of you are like, Dennis, good, I'm pretty good. Right now, I don't like the fact that they're complex numbers, but right now I feel pretty good.
Not too bad right now.
Not too bad. Good. Thank you, Jordan.
Yeah, I'm good.
Good.
Good. Good
Parents?
here.
Terrific. Appreciate that.
I'm good.
Okay. Remember,
Good.
this is not a threat. This is what people in electrical engineering say is, this is the topic that is in electrical engineering designed to flunk people out. It can be hard. I understand that. I get that. But it's just a tool. These complex numbers are just tools. They don't exist in the real world. Now that we know the form of a complex number, I want everybody to know, I hope you laugh over this, you will never go to the butcher at the grocery store and say, I'd like 3 plus J2 pounds of bologna, please. It doesn't exist in the real world. Only real numbers exist. So these imaginary numbers, they don't exist. The imaginary part of these complex numbers, they don't exist. We have a full and thorough understanding of the real part, but right now you're not even sure why we need the imaginary part. So don't worry about that. We have them, we're going to need them, and we're going to use complex numbers as a tool to make solving problems much easier than using the calculus that we would need to use. That's what we're doing. So we're going to use algebra and complex numbers instead of using calculus. That's our goal. Okay. So to that end, we are going to need to know how to do mathematical manipulations with complex numbers. So let's look at mathematical operations. Okay, another quick temperature check on you. I want to know how my pace is for you. Is the pace okay? Am I too fast?
That's good.
Excellent, appreciate that. Please slow me down if I'm going too fast, okay? I can easily do this, right, scrolling around. I don't want to do it too much. I am going to try to save these notes. And for those of you who chimed in a little bit later, I am recording all. My intent is so anybody can serve as a reminder for me, hey, Dennis, did you start the recording? I'm recording all lectures so that you can go back and view all lectures that I have. So to me, that means a couple of things. One is we want to make sure that we have a good connection. Right now, I'm seeing no glitches on the connection. Number two is I want to make sure you can hear me clearly so that if you do go to the video, you'll be able to hear me clearly on the video as well. So please help me on that end for anything that is not working well. That will help you better if you go back and try to look at these videos. Okay, I'm going to start with all very general terms. I know we don't like this. We are engineers, we want numbers, but I'm going to start with very general terms. So for everything that we do, okay, we're going to assume the following. Just assume we have two complex numbers. Assume A is one complex number, and it's going to be A plus JB, and capital B is our other complex number, and it's going to be equal to C plus JD, okay? So those are the two complex numbers. Now, here's what we want to look at. First operation. Operation number one, it's going to be addition, and operation number two is subtraction. It's going to follow this. So operation 1 and 2, subtraction is going to be identical to this. I think you'll see why. So here we go. For addition, we want to know, how do we add complex numbers? So I want to know, how do I add A plus B? A plus B. Well, A plus B is equal to A plus JB plus C plus JD. And this is equal to, now this is addition. All the rules and all of our operations in mathematics hold true. They hold true for this set of all complex numbers, just like they do for the real numbers. So I'm adding things. The first thing I can do is I can remove the parentheses. So here we go. A plus JB plus C plus JD. And then what I'm going to do is I'm going to shift order. That's equal to A plus C plus JB plus JD. And I recognize, obviously, I'm going to group these because I can group if I want to. And then I see the common factor of J, and it's going to be B plus D. So what did we just prove? This is what we proved. That we can add complex numbers. Now, number one, you don't know this, but I'm going to write this right at the top for addition. Always add complex numbers in rectangular form. So you could probably see as a side over here, if I were to try to add these complex numbers like this, like 3 at an angle of 30 degrees plus 2 at an angle of 120 degrees, right now you would have no idea how to add those. We wouldn't know how to do them. So what you would have to do is you would have to convert to rectangular. In order to do this, we only know how to add in rectangular form. And part of this is problematic for us because sometimes we get these problems in this particular format. And then we want to do something with it, but we can't. And the only way we can do something with it is to do the conversion. So look, the conversion is easy. Here's what we proved. Ready? So let's just say up front, let me say I call this C. C is A plus B. Notice what the real part of C is. Anybody tell me how I can write the real part of C? What's it equal to? Obviously, it's equal to this. But what's that equal to?
Little a plus little c.
Okay, good. And little a is the real part of capital A, and little c was the real part of capital B. So this is kind of neat. This is a property that we would hope that complex numbers would have. And I'm saying this seriously, we would hope they would have this property because complex numbers don't always have the properties that we would hope they have. We lucked out. The real part of A plus B is actually equal to the real part of A plus the real part of B. Obviously, the imaginary part of C is equal to the imaginary part of A plus B. And that's equal to, anybody want to chime in and tell me what that one's equal to?
The imaginary part of A plus the imaginary part of B.
Outstanding. The imaginary part of A plus the imaginary part of C, of B. Right? It's this B and that D. Notice B plus D is the imaginary part, not J, B plus D. B plus D is the imaginary part. So that's a real nice thing in addition. Well, what do you think is going to happen in subtraction? So here we have the addition of complex numbers. Scroll down. Gosh, this thing jumps all over the place. Okay, all through that. Slowly scrolling through. Okay, so we have the addition, and we have that the result is that we get a complex number. First of all, it's we want to add those numbers. We're going to add them in rectangular form. Same thing is going to be true with subtraction. We're going to always subtract numbers in rectangular form, and we're going to have that the real part of C and the imaginary part of C are going to be equal to something very similar to this. So here, let's write this. Always subtract complex numbers in rectangular form. Okay, so you can see, here we go. Let C be equal to A minus B. So that's equal to A plus JB minus C plus JD, which equals A plus JB, careful, minus C minus JD. Regroup again. A minus C plus JB minus JD. Take that one more step. Equals A minus C plus J, B minus D. And so there we have it. There's our result. What does that mean? That in subtraction, the real part of C, which is equal to the real part of A minus B, is equal to, I'm sure you can all see it, it's the real part of A minus the real part of B. Same is true with the imaginary part. The imaginary part of C is equal to the imaginary part of A minus B, which is equal to the imaginary part of A minus the imaginary part of B. So those are probably the two easiest, addition and subtraction. Later on, you're gonna hate addition and subtraction because once you learn about multiplication and division, you're gonna like multiplication and division a whole heck of a lot better because they work very nicely in polar form. But let's take a look at that. Let's turn our attention to multiplication now. So here we go. Now, I didn't mention this earlier, but it is critically important for me to mention this right now. So polar form, the polar form is just that. It is a form. It's a mathematical shorthand notation for writing a complex number. And what I'm going to do soon, today or tomorrow, is I'm going to give you a mathematical exact expression that we can use in mathematical equations. But right now, the polar form is just a shorthand notation. Rectangular form is not a shorthand notation. It is a mathematical exactness. A plus JB, all right? It's an exactness. But polar form is only a notation. Only a notation. I should have written that down in our notes. So if you backtrack to where we put down polar form, just make a note that polar form is only a mathematical notation, a shorthand notation. So it would be like any other math notation that you have that isn't an exactness in an expression. Okay. So for multiplication, I'm going to do the same thing. I'm going to look at, let's C be equal to A times B, or just AB. Okay? This is equal to A plus JB times C plus JD. Everybody knows how to multiply when we have something like this. Most of you would use the terminology FOIL. So we're going to FOIL this. This is equal to AC plus A times J times D plus J times B times A plus JB times JD. And I know you can start to see a number of things. So let me clean this up a little bit. First, AC. Anywhere I have a J, I'm going to put that in the front. J, ADs, just so you can see it. Plus J, BA. Did I get that right? BC. This is incorrect. Nobody shouted at me. That's a C. BC. JBC. JBC. Let's clean that up right there. BC. And now look at this last term. JB times JD. Tell me about the J times the J. Minus. J times J is J squared. It's negative. Look what's really cool. When you take this imaginary term right here, this imaginary term, and you multiply it with that imaginary term, when you do that, you end up with something that's this term. I know it's negative, but it is purely real. So what I'm going to do is I'm going to group it with AC, which is also real. Here we go. AC minus BD. Put those all together in parentheses. And then plus J, and what multiplies J? AD plus BC. Unfortunately, this is all we can do. We can't reduce this anymore. And so when you multiply complex numbers that are in rectangular form, here you are, you have a rectangular answer, but you're stuck with this. Obviously, A times C will be a number, B times D will be a number, and you can combine those into a simple number. We'll do an example on this one, since it's worth seeing. But overall, you're left with this. Here's what I'm going to write up top. Right now, I'm just going to write that polar form is easier, okay? Polar form is easier. And we'll see why later on. We don't know why right now, but polar form is easier. Okay? We'll see that pretty soon. Now, this is what I want to do. I want to stop here, though, and look at this. So I want to look at this, and I want to do an example. A equals 3 minus J2. B equals 4 plus J. Okay, I'm going to multiply them. C equals A times B equals 3 minus J2 times 4 plus J. All right. Now I'm just going to follow the rules. Now here's the shortcut method I use. I'm going to encourage you to use it. I'm going to show you with arrows, and then I'm going to reduce the arrows. I know that I can immediately go to the real part. I'll expand this afterwards. I can immediately go to the real part, and I'll do this on the side over here, equals. So the real part is going to come from that times that. So the real part comes from the two reals multiplying each other, and then from the two imaginaries. So if I can do that together, I know I'm going to have 7, and then I'm going to minus J2 times the J is going to give me a positive 2. 7 plus 2, that's going to be 9. And then I know the imaginary part comes from an imaginary term times a real term and an imaginary term times a real term. I know that's where they come from. So I get, with this one, I get a minus J8, and with the other one, with this one, I get a plus J3. So it's a minus J8 plus a J3. That's going to be minus 8 plus 3. So overall, this answer is going to be 9 minus J5. Okay? Now, let me erase those markings that I made. There we go. I'm just going to erase this.
Isn't the first one going to be 12 plus 2?
Yeah, it is 12. Thank you. Thank you, Jack. Appreciate you helping me even from a distance. Okay. So this one is going to be over here. That is 12. It's going to change this here. Let's erase that. Just give me a second. My pad here is operating slowly for a moment. I'm not sure why. Okay, let's get rid of this. And let's get rid of that right there. Okay, now let's go back to the pen. So 12 plus 2 is 14. Thank you, Jack, for chiming in. I appreciate that. So over here, 3 minus J2, 4 plus J. Here we go. So it's equal to 3 times 4 plus J times 3 minus J times 4 minus J2 times J equals 12 plus J3. And many of you will be comfortable doing this in the short term. Minus J8, because if you're like me, you'll make mistakes, and you don't want to make mistakes. That minus, and then the minus from the J squared gives me a plus J2. Grouping those terms together, J2. That doesn't give me a J at all. Gives me a plus 2, not a J2, a plus 2. Okay? So let's get rid of my J right there. Plus 2, all right? And then 12 plus 2 is 14. There's our 14. J3 minus J8 is minus J5. Same exact thing. So that's the process that you would use. Now, even though these numbers weren't given to us, so the question is going to be the following. When I get numbers in rectangular form and I need to multiply, should I multiply them in rectangular form? And the answer is probably yes. Even though polar form is easier, it's going to take you time to convert to polar form. And so I would encourage you to just get a sense of the situation and look at what's easier versus what is harder. Now, what I want to do now, though, is I want to show you that we can look at this and observe something interesting if we know a little bit about trigonometric identities. So I don't know how much you know about trigonometric identities, but we're going to spring a few of them on you today. So here we go. So I'm going to let A be equal to R1 at an angle of theta 1, and I'm going to let B be equal to R2 at an angle of theta 2. So remember, I told you this is R1. I'm going to factor it out right now. R1, and then it's R1 times what? Times cosine of theta 1 plus J sine of theta 1. So there it is. It's in rectangular form. And this is R2 times cosine of theta 2 plus J sine of theta 2. Okay. So right now, I have both of those. They started in polar form. They are now in rectangular form. I know how to multiply in rectangular form, so I'm going to multiply them. So if we do that, with C equals A times B, that's going to be equal to R1 cosine of theta 1 plus J sine of theta 1 times R2 times cosine of theta 2 plus J sine of theta 2. Immediately, pull the R1 and the R2 out front. R1 and R2 are real. They are constants. And real numbers that are constants that multiply complex numbers just scale both the real and the imaginary part. Okay, now the fun part. Here we go. So I'm going to try to do it all together in one shot. So here we go. See if you agree with me. So first, cosine of theta 1 times cosine of theta 2. So that's one of the real terms. Now when I multiply the j terms, the two j's multiplied will give me -1. The j will disappear, and then I'm going to end up with sine of theta 1 times sine of theta 2. Okay, that's all the real part. Then I still have inside of this bracket plus now the imaginary part. So here's a j. I'm going to pull the j on the outside, and I'm going to end up with sine of theta 1 times cosine of theta 2. Sine of theta 1 cosine of theta 2. And then I have plus, now the other term is cosine of theta 1 times sine of theta 2. And then big parentheses, and then my big brackets. Okay? So R1, R2 multiplies all of that. I'm going to underline the real part. That's the real part. This is the imaginary part. Everybody good with that? If not, give me a signal that you're not good with that. You don't know where it came from. Okay, if you are, I know that most of you are not experts. Many of you have not had a course in trigonometry. Some of you do remember some basic identities. I'm going to help you with an identity. So this part right here, that one has an identity. Cosine of theta 1, cosine theta 2, minus sine of theta 1, sine of theta 2 is nothing more than, believe it or not, all of that is cosine. Oh, what happened to my pen? Cosine of theta 1 plus theta 2. Okay? The second one, this one here, believe it or not, plus j, and all of that is equal to the sine of theta 1 plus theta 2. Now we're going to need to know some trig identities. You don't need to know that one. I'm telling you that those are the identities. Okay? Okay, let's shift this upward. So that's what we have. Now, what does that tell me? There's something interesting going on that tells me. So this is C which is equal to A times B. Well, if you think of the following, just pretend I gave you this. If I gave you this, so little scratch pad, and then I'm going to erase it. If I give you X at an angle of Y, do you agree that this is equal to X times cosine of Y plus J sine of Y? I mean, we're using R and theta, but it doesn't matter what we're using. Whether we use R and theta, doesn't matter. So if you agree with that, then the following must be true. If I look at R1, R2, at an angle of theta 1 plus theta 2, that should be equal to R1, R2, okay? Whatever number's out front, and then cosine of theta 1 plus theta 2 plus J sine of theta 1 plus theta 2. Son of a gun. Unbelievable. So what did we just find out? So we just found out C, which is equal to A times B, is equal to R1, R2 at an angle of theta 1 plus theta 2. That means when we multiply R1 at an angle of theta 1 multiplied by times R2 at an angle of theta 2, the answer is multiply the magnitudes and add the angles. R1, R2, theta 1 plus theta 2. So that is not something that you would have guessed, I don't think. When you multiply complex numbers that are in polar form, we multiply the magnitudes and we add the angles. That's why multiplying is much easier in polar form, because it's easy to multiply those two magnitudes together and to just add the two angles. So here's an example. A equals 3 at an angle of 60 degrees. B equals 4 at an angle of minus 25 degrees. A times B is equal to C. That's equal to 3 at an angle of 60 degrees multiplied by 4 at an angle of minus 25 degrees. And that's equal to 3 times 4, 12, at an angle of, add the angles, 60 minus 25, 35 degrees. Pretty soon, you're going to learn why angles are measured incorrectly in degrees. We haven't gone over that yet, but radians are the correct measure of an angle. Degrees are not the correct measure, even though we will continue to use both radians and degrees. Okay, so that's multiplication. What do you think about that multiplication? Everybody good on the multiplication? Okay, so while we are here, I am now going to, before I go to division, I am going to present to you an alternative form of writing a complex number. So we're going to pause here, a little aside, and now an alternative for a complex number. And this is timely. So right now we have 1, we have rectangular form. 2, we have polar form. The first one looks like A equals A plus JB. This one looks like A equals R and theta. And this one is called the exponential form. And this is what this one looks like. A equals R E raised to the j theta. Now let me tell you why I like the exponential form. So remember, this form here, remember that's just in mathematical notation. This one is not. Watch this. Watch now. If I take A equals R1 e to the j theta 1, B equals R2 e to the j theta 2. Watch when we multiply. C equals A times B equals R1 e to the j theta 1 times R2 e to the j theta 2 equals R1, R2, e to the j theta 1 plus j theta 2. Pull out the common factor in the exponent of j, right? We can do that. And if we factor that common factor out, I have the following. That's equal to R1, R2, e to the j theta 1 plus theta 2. And there it is, exactly what we showed. You multiply the magnitudes and you add the angles. And mathematically, this shows us why it's correct. Now, what I will show to you, let's see, what time are we at right now? 1:35, we're winding down in time. So I won't show you today, I'll show you tomorrow. Tomorrow is Euler's identity. And so you don't know this yet, but tomorrow I will prove, that R e to the j theta is equal to cosine of theta plus j sine theta with that R out in front of all of that. More important, what I will really prove is that e to the j theta is equal to cosine of theta plus j sine theta. So we need to prove that. Once we prove that, then all of the work that we've done, all of that up above is all valid once I prove this. Proof coming. That's a bizarre thing. This is known as Euler's formula or Euler's equation. Euler, the great Euler, who that E is named for Euler. It's not for exponential, it's for Euler. Euler proved this, and I will show you his proof tomorrow in class. Okay, great. Well, having done that, since we know that, I'm going to use this form. And I'm going to use this form in division so that we can make division a little bit easier, okay? So here we go in division. Okay, right there. So number 4 is our division. Shrink this down just a bit. I'll try to adjust it. Here we go. Division. So I would also tell you that dividing complex numbers is easier in polar or in exponential form. Dividing is easier in polar or exponential form. Exponential form. I think you can see what takes place. I'm going to do this in both. I'll start off doing this in exponential form. Once we have exponential, exponential comes directly from polar. It's the R value and then the angle. Either the J just fits in there. So R at an angle of theta, R e to the j theta, there's the theta, there's the R. So these two forms are nearly identical. Here we go, we're going to divide. A equals R1 e to the j theta 1. B equals R2 e to the j theta 2. C equals A divided by B equals R1 e to the j theta 1 divided by R2 e to the j theta 2 equals R1 over R2. You all knew that. E to the j theta 1 minus j theta 2, which is equal to, net result, R1 over R2. E to the j theta 1 minus theta 2. What does that tell us? When you are dividing complex numbers, divide the magnitudes, subtract the angles. Subtract the denominator angle from the numerator angle. So multiplication, it's multiply the magnitudes, add the angles. Division, it's divide the magnitudes, subtract the denominator angle from the numerator angle. So that means R1 at an angle of theta 1 divided by R2 at an angle of theta 2 is equal to R1, R2, R1 divided by R2, angle theta 1 minus theta 2. All of these things that I'm telling you are easy to do. They're not easy to understand. So I get we're dealing with complex numbers, and I get that right now you don't even know why we're doing this. Like, Dennis, please tell us why we're doing all this stuff with complex numbers. It's coming. You'll understand it. Just watch how simple what we're doing really is. What's going to change in our circuit analysis, and that circuit analysis is not going to be with real numbers like we've done. It's going to be with complex numbers. And complex numbers are a little harder to work with than real numbers for obvious reasons. But that's the only thing. It's going to simplify the work that we're doing. Okay, let's look at it from this perspective, even though you won't see the beauty of it. So this is what I'm going to do. I'm going to take A equals A plus JB, and I'm going to let capital B equal C plus JD. So you won't appreciate this, but what we're going to do is we're going to take these numbers and we're going to divide them. Now, to divide them will be easier if I explain something to you about a complex conjugate. So I want to define a complex conjugate. So let's define a complex conjugate. You may have seen conjugates before. If you have, they look something like this. And I'm doing the scratch pad up here. I have 3 minus the square root of 2. Its conjugate is 3 plus the square root of 2. And the reason we did that is so that when we multiplied those two numbers together, the radical sign would disappear. So many of you should remember that from your pre-calculus class. Okay. So complex conjugates are different. If A equals A plus JB, A star is defined as the complex conjugate. The conjugate of A conjugate of A is equal to A minus JB. To find a conjugate of a complex number, everywhere there's a J, you change the sign of the J. So if there's a positive in front of the J, you change it to a negative. If there's a negative in front of the J, you change it to a positive. Okay? So example, if B equals 3 minus J2, B conjugate equals 3 plus J2. If C equals J2 times 4 minus J times 3J, C conjugate equals minus J2, 4 plus J minus 3J. All right, everywhere there's a J, you just change the sign of the J from whatever it is, you just change it from a positive to a negative or from a negative to a positive. Okay, now let me tell you an interesting property of multiplying a number by its complex conjugate. Okay, my screen is sort of half frozen here, so just bear with me. I'm not sure why. There we go. Okay, so let's look at, if we consider the following. I want to let A is equal to A plus JB. A conjugate is equal to A minus JB. Watch what happens when I multiply A times A conjugate. So A times A conjugate is equal to A plus B times A minus B minus JB, not plus B. And that's equal to A times A squared, A times minus JB minus A times JB plus A times JB plus B squared. Cancel, cancel, equals A squared plus B squared. Now I'm just going to remind you that the magnitude of A, we call that R, the length of A, R, is equal to the square root of A squared plus B squared. So this is nothing more than R squared. So A is equal to this, which is equal to R at an angle of theta. Okay? So A times A conjugate, what happens is the imaginary part disappears and I get a purely real number. And by the way, purely real numbers have an angle of 0 if you think about them from the complex plane. They have an angle of 0. So purely a real number, and its value is R squared. So that's a nice, nice thing. Now watch how I use that. Here we go. So we're going to divide. Excuse me for one moment. Stacy, I'm in my lecture right now. I'm going to be done in about 5 minutes. Is it anything urgent?
No, I'll just play that.
Appreciate that. Thanks so much.
Okay.
Bye. Okay. So here we go. Last bit of work for today. So we're going to look at A is equal to A plus JB and B is equal to C plus JD. When I divide them, A divided by B is equal to A plus JB divided by C plus JD. So here's the trick. Here's the trick. Multiply by the number 1. The number 1 disguised in a very clever way. I just choose the complex conjugate of the denominator. Okay? Now when I do that, my numerator is going to have all those terms in it. And so here they are. AC, I'm just going to write them down quickly, plus BD. So it's those terms. And then I have, for the imaginary part, plus J. And now I have BC minus AD. Okay? But look at what happens in the denominator. I already know what happens when I multiply this times this. C squared plus D squared. It's one number. One number. So now I immediately have in this form, I have A divided by B is AC plus BD all over C squared plus D squared. That's the real part. Plus J, here's the imaginary part. BC minus AD divided by C squared plus D squared. And I know it's ugly. This is why we don't like doing this. We don't like dividing. But every once in a while, instead of converting back and forth 15 times, it's going to be easier to stay in one format, and you might want to divide in this format. So whenever you're dividing in the rectangular format, you should always multiply by the number 1, but the number 1 uses the complex conjugate of the denominator. Okay? That's how we do that. All right. Let me pause at that for today. And that will sort of describe all of the things that we need to do with regard to division. And we've got everything that we need to know so we can look at some examples and then get into Euler's formula and then start to understand why we even need all of this. So before we part ways, number 1, any questions from anybody? Okay, hearing no questions. Reminder for those who came on late today, or a little bit later. Number one, try to pop in a minute or two early just to make sure everything's up and running when we're utilizing Zoom. That's number one. Let me just stop my screen share here. Okay, so let's chime in a couple minutes early if we can. That's great. Tomorrow I have a critically urgent meeting with our employees to talk about what's going on and how it pertains to them. That meeting is scheduled. We're trying to at least let them know what it means to them about work, et cetera, et cetera, et cetera. That is scheduled with our chancellor. It is scheduled from 11 to 12 Phoenix time tomorrow. I suspect I will probably be a little late. I would encourage you to hang in there and wait for me, and I'll be in. If I get word that it's going to be too long, I will reach out to you some way, somehow, to cancel class. Some way I will manage to do that to let you know, even if I just leave their meeting, get into your meeting, let you know we're not going to meet today. But otherwise, I plan to meet tomorrow. Okay? We had some information out there about that I put in the meeting invite about getting homework to me and how you do that. Look, I'm going to be really lenient right now. Jack, I'm not worried about whether or not you have engineering paper. I'm not worried about that. If you can find it, great. That's excellent. But I'm not losing any sleep over it. Finding your way to get information to me, get your work to me right now, that's important. We need to figure out what we're going to do with regard to quizzes and exams for the remainder of this course. We don't need to answer that question now. We can take time aside tomorrow to do that. But for the most part, right now, things are going as planned. As I wrote in the invite, the Zoom invite, the one thing that I think we're probably going to cancel, unless any of you have brilliant ideas, is that group project, because that was when I really wanted you to have an opportunity to get into our lab, utilize some equipment that we do have here, and do a little laboratory thing that helped expose you to a little bit more of electrical engineering. So it might be wisest for us to put that on hold on the shelf and figure out what we'll do with those points towards your final grade. Okay, last chance for any questions or comments. Seeing all of you staying on mute, that means to me that there are no questions or comments. Look, I appreciate you. We're trying to get education to you in the manner that works. If you don't think that this format works and you think there's a better format to use, please let me know. I am here for you, for your education. So I want to make sure that this works for you. I know that we've had glitches with other things that other people are trying. Jack, I heard from you already that this morning things didn't work so well with your course with Dr. McCrite. I want to make sure things work well. I've tested this. I've run this at least 4 times now, but there are still some glitches that I'm facing as well. We want this to work. If it's not working, you have to let me know. I can't know unless you let me know because it's working on my end, okay? So I'm going to save in the recording. It will be saved. There will be a way that you can retrieve those. Right now, I'm thinking what I'm going to do with that is put them out on Blackboard. I do have a Blackboard shell. I'm not using it for anything, so I might just upload those so you can find them on Blackboard. If you don't want them out there, let me know that too. If you think, complete waste of time, we're not going to do it. But my plan is to save those and to save any of the writing that I have if this Surface Pro works the way that I think it works, I'll be able to save that. Okay, so have a great rest of your day today. Let me know if you have any questions. Right now, your only homework that you have that's outstanding should be getting your report prepared for your project, that written report, which is due this Friday. Okay, so I'm going to sign off here. I will see all of you tomorrow, hopefully at roughly the same time. Have a great rest of your day. Jack, have a good sleep. I know it's about 10 or 11 o'clock your time over there. So I appreciate you, checking in with us, even though you're way off our time zone over here. Have a great day, everybody. Take care.